Hi, I'm Hongjian Wang. I'm very glad to present our work LinGen towards high-resolution minute-length text-to-video generation with linear computational complexity. To the best of our knowledge, our work is the first to achieve pure linear complexity without involving self-attention for high-quality minute-length video generation at large scale. It achieves more than 10 times speed up than the standard DIT while outperforming it in terms of video quality and text-video alignment. We believe our work paves the way to hour-length movie generation and real-time interactive video generation. The motivation of our work is very straightforward. There are various video generative models that can generate photorealistic, high-quality videos, such as VO2, Sora, and MovieGen. However, without video extension, interpolation, or super resolution, their original video length and resolution are limited. Why is it so hard to generate longer videos at higher resolutions? The key reason is that the cost of self-attention layers scales quadratically with respect to the number of pixels in the generated videos. That means a 2-minute 4K video costs 16,000 times more than a 15-second 1080p video, which is almost unaffordable. There are some existing solutions trying to address the efficiency and scalability issue of self-attention layers. Factorized attention decomposes the full self-attention into the attention along spatial and temporal dimensions. However, such a decomposition maintains the quadratic complexity and incurs degraded video quality. Another solution is generating the original videos at low resolution and then applying super resolution to it. This also incurs degraded video quality and can hardly maintain the good texture fidelity. Lots of recent papers also try to use video extension to generate long videos. The high-level idea is generating the next several frames while conditioning on the previous frames. Such a pattern has localized receptive field and fails to ensure long-term consistency, such as a man who disappears in the initial seconds and shows up again in the last several seconds. Let's take a look at the overview of our proposed LinGen framework. We maintained all the other parts of diffusion transformer unchanged, but replaced the self-attention layer with our proposed mate layer. Mate layer is composed of the MA branch and the TE branch. In the next slides, I will walk you through the bidirectional member 2 module, our proposed rotary major scan, temporal swing attention, and the review tokens which enhance extremely long-range correlations. Member was originated from the state space model. As you can see in this figure, state space model is a sequence-to-sequence model with a hidden state memory. We update the hidden state memory with the projected input sequence and its decayed last state, which is controlled by matrix B and matrix A respectively. The hidden state memory is projected to produce output sequence, which is controlled by matrix C. However, since the input sequence is compressed into the hidden state memory, for tokens that are far from each other in the sequence, the correlation between them cannot be precisely calculated by the model. As you can see in this figure, if we want to recover the input sequence, there will be larger degradation for older steps. Member tries to mitigate this issue by compressing the input sequence into the hidden state memory selectively. It adapts the projection matrices A, B, and C that we mentioned before to the input sequence. Thus, it compresses more informative tokens less and compresses less informative tokens more aggressively. Member 2 is generally a more hardware-friendly version of Member. It can be written in the attention format and thus can leverage existing attention optimizations such as X-formers and flash attention. It also natively supports tensor parallelism and sequence parallelism, which makes the model easier to be scaled up. Member 2 further supports much larger memory size than Member 1, mitigating the long-range decay issue. These are the reasons why we use Member2 in our proposed mate layer. We use its bidirectional version to maintain the square sequence transformation matrix that is similar to the square attention map in self-attention layers. However, native member module does not scale well on vision tasks, which is different from its behavior on language tasks. Why? Let's compare the correlation precision across different token distances in the sequence. Self-attention calculates the correlation between each pair of tokens precisely, so it does not have any decay across different distances. For the member module on language tasks, since the input text is natively a 1D sequence, although the correlation precision decays as the token distance increases, such a decay is moderate and acceptable. However, on vision tasks, the member meets the adjacency preservation issue. What's that? For vision tasks, we have 2D tensors and 3D tensors to represent images and videos, respectively. They need to be transformed into sequences to be used as the input to member modules. In this process, those originally adjacent tokens are separated far from each other in the 1D sequences. This is inevitable because one token has 6 adjacent tokens in a 3D tensor, and you can only maintain up to 2 adjacent tokens when the tensor is transformed into a 1D sequence. Considering the long-range decay characteristic of member, this issue will make the correlation between even originally adjacent tokens degrades significantly, severely hurting the quality of generated videos. There are some existing methods trying to address this issue, such as zigzag scan as shown on the left part and hilbert scan as shown on the right part. By alternating between different scan patterns in different layers, these methods indeed reduced the average distance between adjacent tokens and improved the quality of generated images. However, those scan patterns require complex sequence permutation, which is very unfriendly to hardware. When scaled to large 3D tensors to generate high-resolution long videos, they incur significant extra latency, as you can see in the example shown here. Thus, we propose rotary major scan, which achieves the same average distance between adjacent tokens as these scan methods, while being super hardware-friendly and introducing negligible extra latency. How is rotary major scan designed? We investigated the default scanning behavior when reshaping a 3D tensor to a 1D sequence, as you can see at the top left corner. At the highest level, it is spatial major, because we start from the first frame. At a lower level, it is row major, because we start from the first row of the first frame. We call this pattern spatial row major scan. To minimize the distance between adjacent tokens after scanning, we rotate the majors to produce 4 different scan patterns and alternate between them in different block layers. In this way, we achieve the same average distance as the existing spatial scan methods while at nearly no extra cost. Why is the cost of rotary major scan so low? Because it can be easily implemented in a few lines of code by simply reshaping the input tensors. As you can see in the right figure, rotary major scan achieves even slightly lower loss than zigzag scan while being significantly faster. However, this is still not the end of the story. Let's consider 2 times 2 times 2 cube in a 3D token tensor. None of the existing scan methods can place all the 8 tokens close to each other in a single scan pattern. For example, the spatial row major scan can place the first 4 tokens and the last 4 tokens close to each other, but the distance between token 1 and token 5 is huge. This is due to the fundamental limitation that a single token can only have 2 adjacent tokens in the 1D sequence, while each token in the 3D tensor has 6 adjacent tokens: front, back, left, right, bottom, and up. The larger the tensor is, the larger the average distance between the 8 tokens will be. To completely address the adjacency preservation issue, we developed the temporal swing attention. It is a spatial 3D window attention with a small window size that is fixed across different video resolutions and lengths. The spatial window range is small because we only need this slight window attention to deal with adjacent correlations. And the medium temporal window range enhances the consistency of generated videos significantly. The window scope alternates in consecutive layers to break the window boundary. Note that we fix the window size and keep it very small across different resolutions and video lengths, which keeps the cost small and makes it scale linearly with the number of video tokens. Here are the quantitative analyses on the efficiency and performance of our proposed TESA module. The left table shows that theta only leads to marginal latency increment. The y-axis of the right figure measures the minimum average distance between adjacent tokens among k layers after transforming 3D token tensors to 1D sequences. As you can see, our proposed rotary major scan TESA module completely addressed the adjacency preservation issue and reduced the distance to 1. For those extremely long-range correlations, members still experience moderate precision degradation. To compensate this, we deploy review tokens to write the overview of the generated videos into the hidden state memory of member modules before the video tokens are processed. The implementation is very straightforward. We apply average pooling to the video tokens and append them to the beginning of the input sequence. Due to the computation pattern of the member module, these review tokens will natively be written into the hidden state memory before formal video generation starts. The extra cost is marginal since the number of review tokens is less than 1% of the number of video tokens, and our module has linear complexity with respect to the number of tokens. Here is our training recipe. We use a progressive training recipe that gradually increases the sequence length in the latent space. We start from 256p low-resolution text-to-image pre-training, and then transfer the pre-trained checkpoint to text-to-video pre-training. After that, we gradually transfer to higher resolution and longer video lengths. In all the text-to-video pre-training stages, we include a small portion of text-to-image generation training steps to enhance the consistency of generated videos. Furthermore, after pre-training, we fine-tune our model on a small dataset that includes videos with extremely high quality and good motion. Our LinGen model achieves superior efficiency and performance compared to standard diffusion transformers. LinGen generates 512p 68-second 16 fps videos on a single GPU without super resolution, video extension, or interpolation, achieving up to 12 times speed up without sampling distillation. As you can see in this figure, the cost of LinGen scales linearly with respect to the number of pixels in the generated videos, which indicates much better scalability than the diffusion transformer. The longer in duration and the higher resolution the video is, the greater the savings LinGen brings. LinGen achieves linear complexity and significant speed up. But how about its performance? Here are several visual examples generated by LinGen. As you can see, these generated videos are highly photorealistic with very good motions. We also quantitatively evaluated the performance of LinGen in terms of both human evaluation and automatic metrics. According to our human evaluation results, LinGen is not only comparable to the state-of-the-art commercial video generative models, but also outperforms the standard diffusion transformer that has the same size and was trained on the same dataset with the same training recipe. This is kind of surprising. Intuitively, we would consider the linear complexity mate layer as an approximation of the global self-attention layer, but its performance even outperforms the global self-attention layer. Why? Interestingly, we found that LinGen adapts faster to longer token sequences than DIT in our progressive pre-training recipe, which could be the reason why LinGen outperforms DIT in our experiments. As I mentioned before, during pre-training, we start from low-resolution text-to-image generation and then transfer the checkpoint to low-resolution text-to-video generation, and then we gradually transfer to higher resolution and longer durations. In this process, the visual token sequence in the latent space grows longer and longer, from hundreds of tokens to hundreds of thousands of tokens. The loss curves when we transfer checkpoints indicate that LinGen adapts much faster to longer sequences than DIT. As you can see in the example we show here, when we transfer from low-resolution video generation to a higher resolution, the loss of LinGen is very low even at the beginning. This makes the loss of LinGen is lower than DIT during a huge period of pre-training. We speculate such a fast adaptation inherits from the better tolerance for sequence length changes of member modules, which has been observed on language tasks. To further validate the fast adaptation, we selected the early checkpoints in the 512p video generation pre-training stage. The win rate of LinGen is about 80%, which is even higher than the results I exhibited in the previous slide. We also evaluated our model on vBench to obtain automatic evaluation results besides human evaluation. As you can see in this table, LinGen has a similar score to Runway Gen 3 and Clean and outperforms OpenSora 1.2 significantly. while achieving much longer video generation at significantly lower cost. In conclusion, the most interesting finding of our work is that it is not necessary to involve full attention to achieve good performance on video generation. LinGen achieves pure linear complexity with respect to the number of video pixels. Deploying SSMs or any other sequence-to-sequence model with long-range decay encounters the adjacency preservation issue. Our proposed rotary major scan and temporal simulation could completely address this issue at marginal cost and maintain the linear computational complexity. We also used review tokens to enhance the extremely long-range correlations in the generated videos. Compared to the standard DIT, our linear complexity LinGen achieves better video quality and text video alignment at up to 12 times lower cost. If you are interested in our work, feel free to explore more visual examples and details on our project website. Thanks a lot for listening to my presentation.